Good morning. Today we are going to start the chapter Thermodynamics. Introduction. Need for the second law and different statement of the law. The first law of thermodynamics had certain serious limitations. To overcome these limitations, a strong need was therefore felt to introduce another law called the second law of thermodynamics. A few limitations of the first law, and as a consequence, some definitions given to the second law are briefly given below. First, a major limitation of the first law of thermodynamics is that it merely indicates that in any process there is an exact equivalence between the various forms of energies involved, but it provides no information concerning the feasibility of the process. That is, whether the process is possible or not. For example, the first law does not indicate whether heat can flow from a cold end to a hot end or not. All that it tells is that if this process occurred, the heat energy gained by one end would be exactly equal to that lost by the other end. Similarly, the first law does not tell whether a gas can diffuse from lower pressure to high pressure or water can itself run uphill, etc. The second law supplies answer to the above question by stating that all spontaneous processes like the flow of heat from the hot end to cold end, diffusion of gas from high pressure to low pressure, or the flow of water down a hill, etc., are thermodynamically irreversible. First definition. The term spontaneous process used in the above definition means a process which can take place without the help of any external agency. All natural processes, some of which are mentioned in the definition above, are spontaneous processes. However, it may be mentioned here that the term spontaneous does not give any idea of the rate of the process, that is, whether the process takes place fast or slowly. All that it implies is that a process can occur without the help of an external agency. Second, the first law states that when heat is converted into work, the work obtained is equivalent to the heat absorbed. However, it has been seen from experience that the heat absorbed cannot be completely converted into work without leaving some change in the system or the surroundings. For example, the heat produced in a locomotive is not fully utilized in running the train. A part of it is lost to the surroundings or wasted in overcoming the friction. Hence, the second law is also stated as follows. The complete conversion of heat into work is impossible without leaving some effects elsewhere. Second definition. Beside above definitions, a number of other definitions have also been given to the second law of thermodynamics. The two important ones are 1. It is possible to construct a machine functioning in cycles which can convert heat completely into the equivalent amount of work without producing some changes elsewhere. Third definition. Second, without the use of an external agency, heat cannot by itself pass from a colder to a hotter body. Fourth definition. The term functioning in cycles is introduced in the above definition to indicate that the machine must return to its original state at regular intervals so that it can function continuously. Further, it may be recalled that in an isothermal reversible expansion of an ideal gas, delta U is equals to 0 so that Q is equals to W. That is, the work done is exactly equal to the heat absorbed by the system. In other words, in the process, heat is completely converted into the work. However, It is important to observe that this conversion is accompanied by an increase in volume of gas so that the system has undergone a change. A number of other definitions have also been given to the second law of thermodynamics, which we will come across in the succeeding section of this chapter. The fraction of the heat absorbed by a machine that it can transform into work is called the efficiency of the machine. Thus, if Q is the heat absorbed and W is the work done, then the efficiency of the machine is given by N is equals to W upon Q. The machine used for the conversion of heat into work is called heat engine. In order to bring out this conversion, the engine absorbs heat from a heat reservoir at a high temperature, called the source, converts a part of it into work, and returns the remainder to the heat reservoir at a lower temperature, called the sink. Carnot cycle and its efficiency. In order to calculate the efficiency of any heat engine, Sadi Carnot devised a technique in 1824 called Carnot cycle. A cycle is a process in which a system returns to its original state after a number of successive changes. A process conducted in this manner is called a cyclic process. The engine chosen by Carnot, called Carnot engine, for the purpose of the calculation of the efficiency was a hypothetical one and cannot be achieved in actual practice. It was selected because it could be subjected to simple thermodynamic treatment. It consists of a cylinder containing 1 mole of an ideal gas as the working substance and fitted with weightless, frictionless piston so that all the operations in the cycle are carried out reversibly. For this reason, it is also called reversible heat engine. The cylinder is supposed to be insulated on all sides except at the bottom, so that heat can flow to or from the system only through the bottom. Further, it is supposed that there are two heat reservoirs, one at higher temperatures T2 called the source and the other at a lower temperature T1 called the sink. If some operation is carried out by placing the cylinder in the source or the sink, it can exchange heat with it, and hence the temperature remains constant, so that the process is isothermal. On the other hand, if during an operation the cylinder is placed on an insulating material, no heat exchange can take place between the system and the surroundings, and hence the process is adiabatic. The Carnot cycle consists of 4 different operations, which can be represented on a pressure volume diagram, sometimes called as indicator diagram. These operations are carried out as and are briefly described below. First, isothermal expansion. The cylinder containing 1 mole of the ideal gas occupying a volume V1 is placed in contact with the source, the heat reservoir at temperature T2. The gas absorbs heat Q2 from the source and expands isothermally and reversibly till its volume has increased to V2. The path of the process is represented by the isothermal curve AB. Since the gas is ideal, the work done W1 by 1 mole of ideal gas will be given by W1 is equals to RT2 ln V2 upon V1. Further, for an ideal gas, the work done is equals to heat absorbed Q2, so that negative of W1 is equals to Q2 is equals to RT2 ln V2 by V1. Here, W1 has been taken as negative and Q2 as positive by the latest SI conventions of sign. Second, adiabatic expansion. The cylinder is now removed from the source and placed in perfectly insulating material so that the gas now expands adiabatically and reversibly. Work is done in the expansion, but since no heat enters or leaves the system, the temperature must fall. The reversible adiabatic expansion is continued till the temperature has fallen to T1, which is the temperature of the sink. Suppose the corresponding volume becomes V3, the path is shown by adiabatic curve BC. The work done Wt will be given by negative of W2 is equals to Cv whole T1 minus T2, or you can say W2 is equals to negative of Cv bracket T2 minus T1, where Cv is the heat capacity of the ideal gas. Here again W2 is negative by the usual conventions of sign. Third, isothermal compression. The cylinder is now removed from the insulating material and placed in contact with the sink, that is, the heat reservoir at the lower temperature T1. The gas is compressed isothermally and reversibly till the volume decreases from V3 to V4. The process is represented by the path CD. The work done is taken as positive by the usual convention of sign and hence will be given by W3 is equals to RT1 ln V4 upon V3. During the operation, the amount of heat Q1 exactly equal to W3 will be returned to the sink at T1, that is, heat has been given out by the system. Using the appropriate conventions of sign, Q1 will be negative and W3 will be positive, so that negative of Q1 is equals to W3 is equals to RT1 ln V4 upon V3. Fourth, adiabatic compression. The cylinder is now removed from the sink and placed again on the insulating material. The gas is then compressed adiabatically and reversibly along dA till the initial state A is regained. The temperature of the gas rises from T1 to T2. The work done is positive by the conventions of sign and will be given by W4 is equals to Cv bracket T2 minus T1. As a result of these four operations, the system has returned to its original state so that a reversible cycle has been completed. The net work done of the system will be given by the sum of the all four work done which we have done earlier. And at last, after solving the equations, we will get the efficiency of the Carnot engine through the equation W upon Q2, which is the efficiency, is equals to T2 minus T1 upon T2. Carnot theorem. From equation, it is clear that the efficiency of the reversible heat engine depends only upon the temperatures of the source and the sink and is independent of the nature of the working substance. Another important observation is to be made from the above derivation is that the work done in the cycle is only the one involved in isothermal operation, because the work done in adiabatic operations cancel one another. Further, as discussed earlier, the work done in a reversible isothermal expansion is maximum, whereas the work done on the gas during the reversible isothermal compression is minimum. Hence, the total work done by the system is maximum for the specified conditions, and therefore the efficiency is maximum. The result that follows from the Carnot cycle is called Carnot theorem, and it may be stated as follows. The efficiency of a reversible heat engine depends only upon the temperatures of the source and the sink and is independent of the nature of working substance. In other words, all reversible heat engines working between the same two temperatures have the same efficiency. Further, it states that the efficiency of a reversible heat engine is maximum for the given temperatures. Since the quantity T2 minus T1 upon T2 is always less than unity, the efficiency of the heat engine is thus always less than unity. In view of above discussion, the second law of thermodynamics is sometimes defined as follows. A heat engine absorbs a certain amount of heat from the source, converts a part of it into work, and returns the rest to the sink. In other words, it is impossible to convert heat completely into work. Further, combining equations, we get W is equals to Q2 minus Q1. That is, the net work done by the system is equal to the net heat absorbed by the system. So further we get a new equation for the efficiency, that is W upon Q2 is equals to, that is efficiency is equals to Q2 minus Q1 upon Q2, or uh, we have derived it earlier as T2 minus T1 upon T2. This result, derived for reversible Carnot cycle, led to the introduction of a new thermodynamic term called entropy. Concept of entropy as a state function. For a reversible Carnot cycle working between temperatures T2 and T1, it has been seen that Q2 minus Q1 upon Q2 is equals to T2 minus T1 upon T2, where Q2 is the heat absorbed isothermally and reversibly at temperature T2 and Q1 is the heat lost isothermally and reversibly at temperature T1. The above equation may be simplified as Q upon T is equals to constant. Thus, we conclude that heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which the heat is absorbed or lost is a constant quantity for a particular system. Further, in equation, Q2 is the heat absorbed at temperature T2 and Q1 is the heat lost at temperature T1. If Q1 were the heat absorbed at temperature T1, equation 2 would be written as Q2 upon T2 is equals to minus of Q1 upon T1, or Q2 upon T2 is plus Q1 upon T1 is equals to 0. That is, sum of Q upon T is equals to 0. Now consider any reversible cycle ABA. It may be regarded as being made up of number of Carnot cycles drawn across the diagram. Starting from A and going through all the cycles successively from A to B, it can be shown that all paths inside the closed curve ABA cancels each other, leaving only the zigzag path, which is almost the same as the path AB of the reversible cycle. By making each Carnot cycle smaller and increasing their number, it can be made to correspond more closely to ABA. The reversible cycle can therefore be regarded as being made up of an infinite number of Carnot cycles. For each of these cycles we have sum of Q upon T is equals to 0 as proved above. Hence, for an infinity number of Carnot cycle, we have sum of delta Q upon T is equals to 0. Here del Q is a very small quantity of the heat absorbed at temperature T during the small isothermal change of the reversible process. Further, the above term may be divided into two parts, from the path A to B and the other for the back path B to A. This implies that the total value of the quantity Q upon T for the path A to B is equals to the total value of quantity Q by T for the reverse path B to A. Hence, it may be concluded that the quantity q by t is a state function, that is, its value depends only upon the initial state A and final state B and is independent of the path. Obviously, q by t is the change in the value of the quantity or a function having some definite values at A and B, depending upon the values of pressure, volume, and temperature. This quantity or the function is called entropy and is usually represented by the symbol S. Thus, Q by T is equals to SB minus SA, that is del S, where delta S represents the total change in entropies in going from initial state A to final state B. Hence, entropy may be defined as a state function, the change in the value of which from the initial state to the final state is equals to the quantity Q by T, that is, the total heat absorbed reversibly and isothermally in going from the initial state to the final state, divided by the absolute temperature at which the heat is absorbed. From equation 6, the entropy change may be defined directly as the quantity of heat absorbed isothermally and reversibly divided by the absolute temperature T at which the heat is absorbed. It is important to note that as entropy is a state function, therefore the value of entropy change during a process should not depend upon the path, that is, whether the heat is absorbed reversibly or irreversibly during the process. However, since the derivation of the above result is based upon Carnot cycle in which the heat is absorbed reversibly, therefore expression for the entropy change is valid only when the heat is absorbed reversibly. Thus, it is better to use the symbol QREV in place of Q. The expression may therefore written as delta S is equals to QREV upon T. Further, as entropy is a state function, a small change in its value can be expressed as del S. Unit of entropy. From the expression, it is obvious that the units of entropy will be the calories per degree if heat is expressed in calories. Further, entropy is an extensive property. It is therefore important to mention the quantity of the substance involved. It is usually expressed for 1 mole of substance. Hence, the entropy units are calories per degree per mole. If heat is measured in joules, the units of entropy will be joules per degree per mole. Entropy change in a reversible process. Suppose a process occur under completely reversible conditions, that is, the heat is absorbed by the system reversibly and the heat is lost by the surroundings also reversibly. If QREV is the heat absorbed by the system reversibly, then the heat lost by the surrounding will also be QREV. If the process takes place isothermally at the absolute temperature T, then first entropy change of the system will be given by del S system is equals to QREV upon T, and entropy change of surrounding will be given by del S surroundings is equals to minus QREV upon T. Hence, the total entropy change for a combined system and surrounding will be del S system plus del S surrounding, which is equals to 0. Thus, we may conclude that in a reversible process, the net entropy change for the combined system and surrounding is 0. That is, there is no net change in entropy. Entropy change in an irreversible process. If any part of the process is irreversible, the process as a whole is irreversible. Suppose that the total heat lost by the surrounding is QREV. This heat will be absorbed by the system, but the entropy change of the system does not depend upon the heat actually absorbed, but it depends upon the heat absorbed reversibly. that is, on the quantity QRV. Thus, if the heat is absorbed isothermally by the system at the absolute temperature T, the entropy change of the system will be delta S system is equals to QREV. Further, suppose the loss of heat Q irreversible by the surrounding take place infinitesimally slowly, that is reversibly and isothermally at the temperature T, then entropy change of surroundings will be given by delta S surrounding equals to minus Q IRREV upon delta upon T. The total entropy change for a combined system and surrounding will therefore be delta S system plus delta S surrounding, that is Q reversible upon T minus Q irreversible upon T. Now we know that work done in reversible process is maximum for as the internal energy is a state function, the value of del U is the same whether the process is carried out reversibly or irreversibly. Hence, delta U is equals to QREV minus work reversible is equals to heat irreversible minus work irreversible. Combining results, we concluded that Q reversible upon T minus Q irreversible upon T is greater than 0. Thus, we can say delta S of system plus delta S of surroundings will be greater than 0 for the process irreversible process. The entropy change for the combined system and the surrounding is greater than 0. Since all the spontaneous processes are thermodynamically irreversible, first definition of the second law of thermodynamics, it may be stated that all spontaneous processes are accompanied by a net increase of entropy. This is also one of very common statements of second law of thermodynamics. The result for entropy change is in a reversible process, and that in an irreversible process may be combined together and put in the form delta S of system plus delta S of surrounding is always greater than equals to 0, where the sign equal to stand for reversible process and the sign greater than for the irreversible process. The exact calculation of total entropy change during an irreversible process when heat flows from body B at higher temperatures to a body A at lower temperatures when brought in contact with it may be carried out as follows. Suppose the heat lost by the body B is represented by Q irreversible. The flow of heat may be allowed to take place infinitesimally slowly so that it is absorbed by the body A reversibly and isothermally at T1, which may be represented as Q reversible. The entropy the entropy change of the body B will also depend only on Q reversible. Hence, entropy change of body B is equals to minus Q reversible upon T2 and entropy change of body A is equals to plus Q reversible upon T1. Minus sign indicates decrease in entropy while positive sign indicates increase. Thus, delta S total is equals to Q reversible bracket start 1 upon T1 minus 1 upon T2 bracket close. The combined system and the surrounding is sometimes called an isolated system. The result derived in section 2.6 and 2.7 are thus for an isolated system. Negative sign with work has been used as it is work of expansion. Glacius inequality. As discussed above, for the irreversible process, the result given in equation 9 may be written as delta S system plus delta S surroundings is greater than 0. Thus, delta S system is greater than negative of delta S surroundings. And we have delta S surrounding equals to minus Q upon T. Thus, delta S system is greater than Q upon T. For small changes, the above equation may be written as del S system is greater than minus del S surrounding and or del S system is greater than del Q upon T. These expressions are called Euclidean inequality. These equations show that irreversible processes are accompanied by increase of entropy. This is further illustrated with the help of following two examples of irreversible processes. First, spontaneous expansion. A. Irreversible adiabatic expansion. Suppose the system undergoes irreversible adiabatic change, then dq is equals to 0. Hence, by Clausius inequality, del S system is greater than 0. That is, entropy of the system has increased. Further, as dq is equals to 0, this means that no heat is transferred into the surroundings. Thus, del S surroundings equals to 0. Hence, total entropy change ds total is equals to ds system plus ds surrounding is equals to ds system. B. Irreversible isothermal expansion. We know that when a perfect gas expands isothermally, its internal energy remains constant. That is, del U is equals to 0. Hence, according to the first law of thermodynamics, del U is equals to del Q plus del W. Del Q plus del W is equals to 0, or del Q is equals to minus of del W. If the gas expands freely into vacuum, no work is done, so that dW is equals to 0. Substituting in equation gives dq is equals to 0. Hence, by Clausius inequality, del S system is greater than 0. Further, as dq is equals to 0, this implies that ds surroundings equals to 0. Hence, the total entropy changes just as in the above case, that is ds is greater than 0. Second, spontaneous cooling. Suppose heat is transferred from one system at a higher temperature T2 called the source to another system at lower temperature called T1 called the sink. If heat dq leaves the source and enters the sink, then entropy change of the source equals to minus dq upon T2, or entropy change for the sink is equals to dq upon T1. Therefore, total energy change ds total equals to dq t upon t1 minus dq upon t2 equals to dq bracket 1 upon t1 minus 1 upon t2. Entropy change of the universe. Since all spontaneous processes occurring in nature are thermodynamically irreversible, these accompanied by increase of entropy. Hence, it may be concluded that entropy of universe is continuously increasing. This result is sometimes taken as another statement of second law of thermodynamics. Thus, the main ideas of the first and the second law of thermodynamics may be summed up in the following statement. The energy of universe is constant, whereas the energy of universe is continuously increasing and tends to a maximum. Entropy for an ideal gas with change in pressure, volume, and temperature. Consider 1 mole of an ideal gas enclosed in a cylinder fitted with a frictionless piston. If infinitesimally small amount of heat del Q reversible is opposed to the system reversibly and isothermally at temperature T1, then the entropy change accompanying the process will be given by, according to first law of thermodynamics, for an infinitesimal process, del Q is equals to du minus del W. If the process is carried out reversibly, equation 2 may be written as del Q is equals to du minus del W. This is equation 3rd. Further, if the work is restricted to the work of expansion, as in usually the case of for the process considered in chemical thermodynamics, then minus del W is equals to PdV, where dV is the small increase in volume and P is the pressure of the system, which is nearly equals to the external pressure because the process is carried out reversibly. Putting the values, we get del Q reversible equals to du plus PdV. Substituting this value in equation 1, we get ds equals to du plus pdv upon t, or may be written as TdS equals to du plus pdv. Now for 1 mole of an ideal gas, we know Cv is equals to du upon dt, that is du is equals to Cv dt, where Cv is the molar heat capacity at constant volume, and PV equals to RT, that is P is equals to RT upon V, that is ideal gas equation, where V is the volume of the system at temperature T1 and pressure P and R is the gas constant. Putting the values Tu and P from equation 7 and 8 in equation 6, we get TdS equals to Cv dt plus RT upon V dV. ds, or we can say ds equals to Cv dt upon T plus R dV upon V. This is equation 9th. If the volume changes from V1 to V2, then the temperature changes from T1 to T2. Then the entropy change accompanying the complete process will be given by integration S1 to S2 ds equals to integration T1 to T2 Cv dt upon T plus integration V1 to V2 R dV upon V. Assuming that Cv remains constant in temperature range T1 to T2, equation may be written as delta is equals to Cv ln T2 upon T1 plus RT R ln V2 upon V1. This is an expression for the calculation of entropy change of 1 mole of an ideal gas accompanying a process when temperature change from T1 to T2 and the volume changes from V1 to V2. Further, for 1 mole of an ideal gas, we may write P1 V1 equals to RT1 for initial state and P2 V2 equals to RT2 for the final state. Dividing equation 13 by 12, we get P2 V2 upon P1 V1 equals to T2 upon T1, or we can say V2 upon V1 equals to T2 P1 upon T1 P1 P2. Putting these values, we get del S equals to Cv ln T2 upon T1 plus R ln T2 P1 upon T1 P2. Further, we know that Cp minus Cv equals to R, or Cv is equals to Cp minus R. Thus, delta S equals to Cp minus R ln T2 upon T1 plus R ln T2 P1 upon T1 P2 equals to Cp ln T2 minus T2 upon T1 minus R ln T2 upon T1 plus R ln T2 upon T1 plus R ln P1 plus P1 upon P2, or del S equals to Cp ln T2 upon T1 plus R ln P1 upon P2. This is an expression for the calculation of the entropy change of 1 mole of an ideal gas accompanying a process when temperature changes from T1 to T2 and the pressure changes from P1 to P2. Entropy change of an ideal gas is in different processes. Equation 11 gives the entropy change for 1 mole of an ideal gas when temperature and volume are variables. Similarly, equation 16 gives the entropy change of 1 mole of ideal gas when temperature and pressure are variable, and these equations are modified if the condition of a constant temperature, pressure and volume are imposed. For example, if temperature is kept constant, that is for isothermal process T1 equals to T2, equation are reduced to delta S equals to R ln V2 upon V1 is equals to R ln P1 upon P2. Alternatively, these expression can be derived directly as follows. Delta S is equals to Q reversible upon temperature minus W maximum is equals to Q reversible equals to nRT ln V2 upon V1 nRT ln P1 upon P2. Substituting values QRV from equation 19 and 20 in equation 18 and putting n equals to 1 for 1 mole of ideal gas, we get the result. Second, if pressure is kept constant, that is for isobaric process, P1 equals to P2. Equation 16 is therefore modified to del S equals to Cp ln T2 upon T1. Third, if volume is kept constant, that is for isochoric process, V1 equals to V2, equation 11 is therefore reduced to del S equals to Cv ln T2 upon T1. Note carefully that all expressions derived from above calculation of entropy change involve natural logarithms. Since logarithmic tables commonly used are to the base 10, in applying these formula, ln x has to be first replaced by 2.303 log x, where x is a quantity like t2 upon t1, v2 upon v1, etc. Further note that if a gas expands reversibly but adiabatically, then as for such a process q reversible equals to 0, therefore delta S equals to 0. Entropy change during physical change. Phase change. A change of phase occur in any one of the following cases. First, when solid melts, or conversely when a liquid freezes. Second, when a liquid evaporates, or conversely when a gas condenses. Third, when one crystalline form changes into another. When the change of phase commences, the temperature remains constant till the change of phase is completed. The heat evolved or absorbed during the phase change thus does not change the temperature and is therefore called latent heat. It is further termed as latent heat of melting, latent heat of vaporization, etc., depending upon the nature of the process involved. In general, if del LH is the latent heat and T is the temperature at which the change of phase occur, the entropy change accompanying the phase change will be given by delta S equals to del LH upon T. The entropy change delta S is termed as entropy of melting, entropy of vaporization, etc., depending upon the nature of the process. For example, we have first entropy of melting or fusion, delta S F equals to delta fusion heat H upon Tf, when delta FUSH is the latent heat of fusion, that is melting, and Tf is the melting fusion temperature. Second, entropy of vaporization, delta SV is equals to delta vap H upon TB, where delta H vap H is the latent heat of vaporization and TB is the boiling temperature. It may be mentioned here that the process like melting and evaporation involve absorption of heat, which is taken as positive by convention of sign. Therefore, delta S for these processes positive. That is, these processes are accompanied by increase of entropy. On the other hand, the reverse processes like freezing and condensation involve evolution of heat, which is taken as negative. Therefore, for the processes delta S is negative, that is, these processes are accompanied by decrease of entropy. It may also be remembered, as discussed earlier, that if heat is measured in calories, The units of entropy change are calories per degree per mole. If heat is measured in joules, the unit will be joules per degree per mole. Now, physical significance of entropy, measure of disorder. An examination of the various processes which are accompanied by a net increase of entropy shows that they are associated with an increased randomness of distribution. For example, first, the melting of a solid is accompanied by a net increase of entropy, and at the same time we know that the molecules, atoms or ions in a solid have fixed positions and they become free to move about in the molten state. This is expressed by saying that there is no disorder among the molecules, atoms or ions in the solid, but the disorder set in when the solid changes into liquid. In other words, it is stated that the randomness has increased. Second, the vaporization of liquid is accompanied by a net increase of entropy, and at the same time the disorder or the randomness also increases because the molecule of vapor are more random than the molecules in liquid. Third, heat magnetized iron needle demagnetizes it because the molecules of the magnetized iron needles which were oriented in a particular fashion loses the order on heating and becomes disorder. That is, randomness increases. Fourth, all spontaneous processes like diffusion of gases, flow of heat from the hot end to the cold end of an iron bar are accompanied by a net increase of entropy as well as an increase of randomness or disorder. For example, in the phenomena of diffusion, the two gases which are separated initially get mixed up in a random manner. Similarly, in the flow of heat, the electrons present on the hot end and having higher kinetic energy rush to the cold end, thereby making the distribution more random. Hence, it may be concluded that entropy is a measure of randomness or disorder of the system. This concept may be further understood with the help of the following examples. In a college, first example, in a college, when all classes are being held, all the students are sitting in their respective classrooms and the disorder is minimum. As soon as the bell goes, the students of the different classes come out to go to other rooms and thus get mixed up. In other words, the disorder or the randomness increases. Second, in the game of hockey or football, to start with, all the players take up some definite positions and thus are said to be in order. As soon as the game starts, the players start running and thus they are said to have an increased randomness which increases further as the game catches more and more momentum. Hence, here was the completion of our chapter. Thank you.